Hello everybody, I am Nagesh Prabhu, Professor and Head Department of Electrical and Electronics Engineering, NMAM Institute of Technology, NETE. So let me take you to the world of three-phase generators, which are called as synchronous generators. Synchronous generator is a AC generator, and in the simple term, generator is a machine which converts mechanical energy into electrical energy. AC generator converts mechanical energy into alternating current electrical energy. AC generator is also called as alternator. For any alternator, we require to run that alternator making use of prime mover, which produces mechanical energy. Prime mover can be anything, and it can be a diesel generator, hydraulic turbine or steam turbine. This slide will give the pictorial view of a diesel engine driven alternator. Here is the diesel engine, and this diesel engine drives this alternator, and normally the speed of the diesel engine is in the order of 1500 rpm. In the second case, the prime mover can be a water turbine, and in the case of water turbine, the water is allowed to impinge on the blades of the water turbine, and the blades of the water turbine are called as Pelton wheel. It is a class of turbine wherein kinetic energy and potential energy of the water is utilized to produce mechanical energy, and the water with kinetic energy and potential energy is allowed to impinge on the blades of the turbine. This water wheel or Pelton wheel is going to rotate in this direction and causes the production of mechanical energy. And in this figure, water turbine is connected to the alternator. This is the alternator, and hence mechanical energy produced by water wheel generator is driving this alternator or synchronous generator, and this in turn produces electrical energy. For every alternator, the kVA rating of the alternator is proportional to d square. So here it should be square, so d square into L, where d is the diameter of the rotor, L is the axial length of the alternator stator, and usually the Pelton wheel or water turbine is running at a low speed which is about 300 rpm. For a given frequency, in our country the nominal frequency is 50 hertz. For a given frequency, there are large number of poles required in order to produce the induced EMF at the given frequency. So, in order to accommodate large number of poles, we require to have large diameter, and water wheel driven alternators are characterized by large diameter d and small axial length, because it has to finally satisfy this equation wherein kVA rating of the alternator is proportional to d square into L. So, if the d is large, L to be small. In the other case, this water wheel driven alternator is usually driven through the water what is impinged onto the blades of the turbine, and let us see how this entire setup is utilized in the case of a hydroelectric power plant. Here is the dam which holds the water in the reservoir, and water from the reservoir is brought to the generating station through these penstocks. Penstocks are nothing but the huge pipes which bring water, and when the water flows from the reservoir, usually reservoir is at a higher level, and this generating plant is at a lower level. So, there is always a difference in the height between this reservoir and the generator station, and the difference between these two is called as head. And if the head is high, the potential energy of the stored water is high, and whenever this water is flowing through these penstocks, the potential energy and the kinetic energy of the water is going to drive this alternator's Pelton wheel and produces mechanical energy, which in turn drives this alternator, and alternator in turn produces electricity, and the terminals of alternator when connected to this transformer is going to step up the voltage, and this stepped up to voltage is further connected to the power lines, and the power is transmitted from generating station to the load center. So, this setup of hydroelectric power plant is self explanatory, and let us see what exactly is going to happen in the case of steam power plant. In the case of steam power plant, usually the speed of the steam turbine is very high, and in the case of steam turbine, as shown in this figure, steam is going to enter through this, and high pressure steam what is so flowing is going to be expanded at various stages of the steam turbine, where the pressure is decreased and the volume is increased, and finally the expanded steam is going to come out of this steam, and the steam what is leaving from here is going to be cooled, and this cooled steam is going to be converted to water, and this water can be again converted to steam. The mechanical power produced by this steam turbine is going to drive this generator, which is in turn producing electrical energy, and this electrical energy can be utilized for driving various loads. In the case of turbo generators, the steam turbine is the prime mover, which is running at very high speed in the order of say about 3000 rpm, and at such high speeds, when this rotor of the turbine generator is rotated, no part of the rotor should be projected outside, because if the diameter is large and if some part of the rotor is projected outside, there will be large centrifugal forces acting onto this rotor, and in order to avoid that, usually the diameter of the turbo alternator is very small, and you can see here none of the part of the rotor is projected outside. So, we call such a kind of rotors as smooth cylindrical rotors. So, let us see more about smooth cylindrical rotors little later, and in order to produce given KVA rating, as discussed earlier, KVA is proportional to d square L. So, since the diameter is very large, since the diameter is very small here, the axial length should be very large in order to meet the KVA requirement. And let us look at the history of alternators. The operating principle of electromagnetic generators was discovered in the early years of 1831 to 1832 by Michael Faraday. The principle later is called Faraday's law, and it states that electromotive force is generated in an electrical conductor which encircles a varying magnetic flux. In the case of alternating current generator, it is well known from the Faraday's laws, and which is the original discovery of the Michael Faraday, which causes magnetic induction of electric current. First 3-phase AC generator is built by C.S. Bradley in the year 1887. Here is the picture of the first 3-phase AC generator which is invented by C.S. Bradley. The alternators are often called as synchronous generators if the alternator is connected parallel to the power system grid. Power system grid is nothing but a group of generators which are already operating, and the alternator what we have at our premises is to be connected in parallel with the power system grid. And once such a alternator what is in our premises which is connected to the power system grid, then such a generator which is a AC generator or else alternator is often called as a synchronous generator, and the word synchronous here is originated by the two group of words syn, which stands for equal, and chronos, which stands for time. So, that is, in a synchronous generator it is always called as synchronous because the mechanical shaft speed is directly related to the power system grid frequency f, and the speed of the synchronous generator in steady state should be given by 120 f by p, where f is the frequency, p is the number of poles for which the alternator is designed. If the AC generator in our premises say is operated individually without being connected to the grid frequency, it can always be called as an alternator, and its frequency can be independent of the grid frequency. And here is the difference between a synchronous generator and the alternator. Often they are same, the only difference is whether we connect this alternator to grid or whether we operate this alternator at our premises individually without connecting to grid. Let us see the principle of synchronous generator. Synchronous generator operates on the fundamental principle of Faraday's laws of electromagnetic induction. Whenever the armature conductor cut across magnetic lines of force, an EMF is induced in the conductor. This is the principle of alternator or synchronous generator. So, let us look at here. Here is the magnetic field which is produced by the field poles, and around this field poles the field winding is wound, and the field winding is further connected to a DC source which produces electricity and the current that is flowing through this field winding, and hence it produces field excitation, and these poles turn out to be electromagnets and further producing the magnetic field. In such a magnetic field, if a coil is driven mechanically, the conductors cut across magnetic lines of force and an EMF is induced in the conductor, and these two poles are, say this is north pole and this is south pole, the direction of field is always from north to south between the poles, and the armature conductors when being rotated cut across magnetic lines of force, and the direction of induced EMF or the induced current is different when the conductor move past under different poles. So, here are the two slip rings for which the ends of the coils are connected, and you look at the AC output what is being tapped from these two slip rings, the direction of current at these two terminals is always alternating, and this is this simple slide which gives you the principle of a AC generator. And whenever the EMF to be induced, definitely there should be a relative motion between the conductor and the magnetic field. The induced EMF is called as dynamically induced EMF. The EMF induced in the conductor only if there is a relative motion between the conductor and the flux. If the conductors are stationary and definitely there is no EMF whatever induced. The direction of induced current can always be obtained by Fleming's right hand rule. So, let us stretch the right hand, thumb indicating the movement of the conductor, forefinger directs the direction of magnetic field, and induced current is always given by the current induced in the conductor. The direction of this induced current is always pointed by this middle finger. Let us see how we can use our right hand in order to determine the direction of current. See, here we have a magnetic field. This is north pole, this is south pole, and the direction of field is always pointed by this forefinger. So, forefinger indicates the direction of field, that is from north to south. So, forefinger is pointing the direction of field, and thumb is pointing the direction of motion of the conductor. So, this is the direction of motion. Suppose if I use this conductor and move it up, thumb indicating the direction of this movement, and this middle finger is going to give us the direction of induced current, and hence the direction of induced current is from this point to this point in this conductor. Synchronous generator is basically an AC machine which has a field winding supplied by an external DC source which produces the magnetic field. It also has an armature winding in which an EMF is induced. As far as the constructional features of the alternator, there are two types of construction. In alternators, we can construct based on whether the field winding is stationary or whether the armature winding is stationary. In first case, we have stationary field winding and rotating armature winding. The construction of this type is similar to the case of a DC generator, and this type of construction suits only for small capacity alternators of a few kilowatt rating. It is because when the armature windings are rotated, we need to collect the current from the armature, and if the size of the alternator is very large in the order of megawatt size, definitely the current to be collected will be in the order of a few kilo amps, and it becomes extremely difficult to design the brushes for carrying such a large current, and hence stationary field winding and rotating armature winding is definitely not suitable for megawatt size machines, and this type of construction is restricted only for few kilowatt rating. Let us see the other type of construction. Stationary armature winding is used here and the field winding is rotated, and such construction is suitable for megawatt size synchronous generators. Let us see more about constructional features in the next slide. Here we have a rotating armature. Rotating armature is shown here, and we have a stationary field winding as shown here. We have 4 poles, and around the poles we have wound the field winding or field coils, and all these field coils are connected in series and further supplied with the DC supply. Now, whenever DC current is flowing through these field winding, they produce north and south poles alternatively and produce the magnetic field, and the flux between these two poles are being cut by the conductors of the armature, and armature conductors are housed in this armature. You can see here, these are all armature slots, and all these slots receive armature conductors, and the systematic connection of all these armature conductors forms the armature winding. And for a 3-phase generator or 3-phase alternator, we have 3 windings, and always the 3 windings are star connected. So, we require 4 brushes, 3 for 3 phases and 1 for neutral. So, these 4 brushes are pressed against slip rings. So, we require 4 slip rings here in order to collect current that is produced in this rotating armature. As I said previously, the current collection becomes extremely difficult when the currents are in the order of few kilo amps, and then this current collection causes large sparking. So, when the magnitude of current is very high, and such kind of construction is not suitable for megawatt size machines. As the principle of alternator says, there should be a relative motion between the conductor and the magnetic flux. So, here we have armature conductors which are stationary and the magnetic field is being rotated. So, rotor contains large number of poles and only 2 slip rings are required here, because we need to provide DC supply through these slip rings, and we require only 2 slip rings for plus and minus terminals of the DC supply. So, whatever the EMF that is produced in stationary armature is being directly available. You can see here there are 3 wires, these are the ends of armature windings, and we can directly obtain 3-phase supply without any current collection devices, because armature winding is stationary. So, this type of construction is best suited for megawatt size machines. Stationary armature conductors, this figure shows little elaborate details. So, here is the stator core. Stator core has slots, and these slots receive armature conductors, and this is the rotor wherein only 4 poles are indicated, and around the pole core, this is pole core, around the pole core we have field coils, and all these field coils are connected in series and further connected to these slip rings, and slip rings are further connected to DC supply via the brushes. So, as discussed earlier, the output 3-phase power is directly obtained from the stator without the use of slip rings. Let us see what are the advantages of stationary armature. Insulation of stationary armature conductors, usually armature conductors are working at very high voltages in the order of 11 kV. So, insulating such armature conductors becomes easy if these conductors are provided in the stationary armature. So, insulation becomes easy. In the second point, tapping of electrical energy at high voltage and high current from a stationary armature is simpler. It is simpler because we do not have to use any current collection devices or slip rings in order to tap electrical energy. So, because the terminals are directly available in the stationary armature. Use of slip rings and brushes for high voltages, high current armature are eliminated, as the load is directly connected to the alternator terminals. But we do require 2 slip rings in order to supply DC power to the field winding. So, low voltage about 600 volts, low current DC field winding is housed in the rotor, and it is easy to insulate such low voltage winding, and it is easy to supply low current through 2 slip rings for the field winding. The machine can operate at high speeds, and this enables a larger output from the alternator. Hence, all alternators are invariably have stationary armature and rotating field winding. Let us see the construction and main parts of the alternator. Alternator or synchronous machines are having two main parts, one is rotor, the other is a stator. Rotor houses DC field winding and this forms a rotating electromagnet. AC windings are mounted on the stator and they result in three phase AC stator voltages and currents. The stator is laminated usually. Lamination of a stator is achieved in order to reduce the losses, and usually we make use of cold rolled grain oriented silicon steel laminations, and all these laminations have a slot cut in the inner periphery in order to receive armature windings. So, this figure shows armature windings, those are housed in stator slots. Slots are usually insulated because these conductors to be insulated being touched to the iron part. So, all these slots are insulated and these windings are housed in the insulated slots. So, let us see how the coils are being inserted. When all the slots are insulated using insulation paper, the class of insulation paper or the quality of insulation paper that is used depends on the rating of the machine and what permissible temperature rise is allowed, and higher the temperature rise that is to be allowed, we have to wisely select the type of insulation material which can suit to the requirements of the temperature rise. When the coils are wound using former, the wound coils can be inserted from one end and it can also be inserted at the other end. Once we complete finishing all the coils inserted and few slots, the other coil end is not being inserted and we can insert it at the end. And there are various types of slots. So, slots can be wide open slots, semi closed slots and closed slots. Wide open slots are mainly used with the high power or higher capacity synchronous generators. So, because in higher capacity synchronous generators, the conductor size is very large or the area of cross section of the conductor that is required is very large. Such large cross section conductors can be easily inserted through wide open slots, and once the conductors are inserted, we can close this using a wedge or the fiber what is best suited for closing these slots. Semi closed slots are definitely used for lesser capacity or smaller capacity alternators, where the area of cross section of the conductor is not that high as compared to the megawatt size machines. So, semi closed slots are mostly used in low kilowatt rating alternators. The other class of slots are closed slots. In such slots, winding coils cannot be inserted, whereas the conductors to be needled through these closed slots. That means, the conductor to be inserted from one end and it should be drawn from the other end, reinserted from the other end and it should be pulled from the first end. So, this type of winding is cumbersome and requires a lot of skilled manpower, and definitely it is not much used in practice. When the stator winding is completed, it looks something like this. The three phase armature winding is formed by interconnecting various armature conductors in the slot spread over the periphery of the stator of a synchronous generator. So, this is a three phase winding. So, in three phase synchronous generators, we have three sets of coils which are displaced by 120 degree phase difference, which is electrical degrees, and these three sets of coils which are provided in this winding, the ends of the windings can be brought outside, and as all of you know, the three windings can be connected either in star or a delta, but in the case of alternators it is invariably star connected, because if the windings are connected in delta, it causes third harmonic currents to be circulated in the winding, and which is not really used. So, unless specified otherwise, all the alternators are star connected, and we are bringing out 4 leads pertaining to 3 for phases, 1 for neutral, for in order to enable this alternator to supply for 3 phase loads and also for single phase loads. The windings can be single layer winding or double layer winding. So, first let us focus on single layer winding. As I said earlier, the slots are receiving the armature conductors, and all these armature conductors are arranged in only one layer. That is why we called such a combination as single layer winding, and these slots are insulated as shown here, and this is the fiber wedge which is used to close the opening of the slot, so that when these conductors are carrying current or at any point of time, these conductors should not come out of the slot. So, we are going to use a fiber wedge here, and since it is only one layer, all the conductors are being arranged. Suppose if we have 36 slots, then we can insert only 18 coils, because each coil has 2 coil sides and one coil side can be inserted in one slot. So, we have 36 slots and we can accommodate only 18 coils, and here is the arrangement of coils for single layer winding, and you can see one coil is having 2 ends or 2 sides. One side of the coil is inserted fully in one slot, the other coil side is inserted in the other slot. Distance between these 2 coil sides is called as coil span. So, more about coil span we can discuss in the next section. In the case of double layer winding, we have all the conductors which are housed in this slot are arranged in 2 layers, and there is a insulation paper you can see here. This insulation paper separates the 2 layers, and since 2 coil sides can be housed in one slot, we can have as many coils as the number of slots. In our earlier example, we have taken 36 slots, we can have 36 coils in the case of a double layer winding. And the double layer winding, as you have seen here, see this is the bottom layer and there is a space wherein we can provide one more coil side. So, every coil side is having one bottom layer and one top layer. So, 2 coil sides can be arranged in 2 layers in the case of a double layer winding. When it comes to the rotor of a alternator, synchronous machine or alternator have rotating electromagnets invariably as discussed earlier, and they are built to have as many poles as produced by the stator windings, and DC currents flowing in the field coils which are surrounding each pole, they are responsible for magnetizing the rotor poles. The magnetic field produced by the rotor poles locks with the rotating stator field, so that rotor and the stator field rotate in synchronism. There are always 2 types of rotor. First type is salient pole type rotor, or we also call them as projected pole type. The other class of rotor is non-salient pole, or we can also call such a class of rotor is smooth cylindrical rotor. In the case of salient pole rotor, this is the case or class of rotor which is mainly used with hydraulic turbines. As we have discussed earlier, hydraulic turbine rotates at low speeds. The speed of the turbine is in the range of 50 to 300 rpm, and when speed is very less here, we require large number of poles for a given frequency to be produced. For example, if we take frequency what is to be produced is 50, then P is given by 120 into F divided by N, where Ns is the speed of the rotor. So, 120 into 50 divided by say 300 if we take, then number of poles that is required is 20. So, here in this figure there are 10 poles, that means speed at which the alternator to be driven in order to produce 50 hertz of frequency should be 600 rpm. So, large number of poles are required on the rotor in the case of low speed alternators, and in order to house large number of poles, we require the diameter of the rotor should be very large. And as we have discussed earlier, when diameter is large, for a given kVA to be produced, kVA is proportional to d square L. So, if diameter is large, then axial length of the stator should be small. So, salient pole type rotors are mainly built with hydraulic turbines or hydroelectric generators, and they are characterized by large diameter and small axial length. So, these points we have already discussed. The ends of the field winding are connected to the DC supply through two slip rings and brushes. Hence, to accommodate more poles, salient pole rotors have large diameter and small axial lengths. So, this is a picture wherein 4 poles are used. Again, the poles are salient in nature. Salient means poles are projected outside, and you can see the air gap between the stator inner periphery and the pole face, they are not constant. So, air gap is varying here, and when air gap is non-uniform, the salient or projecting poles are made of thick laminations, and all these laminations are riveted and they are fixed to the rotor cores. And since the field winding is concentrated winding, so that means large number of turns are wound around this pole core, field winding is concentrated, and we know that if the flux density distribution in the air gap is sinusoidal in nature, we get sinusoidal induced EMF. So, we have to see that the air gap flux density varies according to a sinusoidal rule. The difference between pole face curvature and stator creates non-linear variation in flux across pole face. So, we can see here the reluctance of the path is different at different points. At the polar axis, that is at the middle of the pole, the air gap is very less, and when we move from midpoint of the pole towards the pole tips, the air gap is more, and this causes a higher reluctance at the pole tips and decrease in flux density distribution. So, flux density is maximum at the polar axis, and when you move toward the tip, flux density is decreased. And this non-linear variation of flux across the pole face produces sinusoidal change in the induced EMF. You can see here the flux density distribution is more or less sinusoidal by designing the pole phase profile to vary according to a sinusoidal rule. In the case of cylindrical type rotor, alternators with cylindrical rotors are typically found in high speed steam turbine driven turbo generators. So, here we cannot have a large diameter, because large diameter causes surface speed very high and large centrifugal forces are acting onto the rotor if the rotor parts are projected outside. So, you can see here none of the rotor part is projected outside, and you can see slots what are provided here, they are all receiving armature, they are all receiving field winding, and field windings are connected in such a fashion that the flux density distribution is made to vary sinusoidally. You can wonder, see, air gap remains constant here, but we know that flux density distribution to be made sinusoidal in order that induced EMF to be sinusoidal. So, the number of turns in various field coils here, they are all designed in such a way as to cause flux density is maximum in the d axis or direct axis or the polar axis, and when you move from polar axis to interpolar axis, you will have reduced flux density, though you have constant air gap throughout the periphery of the rotor. So, if the turbine, that is steam turbine, is driven at 3000 or say 1500 rpm, then we require only 2 or 4 poles accordingly. So, this is about the cylindrical type rotor, and here you can see the variation of flux density from interpolar to polar axis. This is polar axis and here is interpolar axis, and here is the rotor which carries field windings, and field windings are all connected together, and finally they are connected to 2 slip rings, and DC current is fed in and out through 2 brushes which are pressed against these 2 slip rings. So, we also get, although the air gap is uniform, non-linear variation of flux around the rotor surface, and we get sinusoidal change in the induced EMF. So, we will stop here, and more about the construction and working of the synchronous generators we will discuss in the next class. Thank you.